Sorry about that. All right, so now we're recording. All right, so let me just remind you, and we're going to introduce these terms, Markovnikov and anti-Markovnikov, which I hate, but I'm going to introduce them, and I'll explain why I hate them. But I'm going to introduce them so you know, so you're not confused when you read the book. Okay, but just by way of introduction, we said last week when we were doing, HX addition. Okay, and again, I'm color coding the hydrogen so we can see where exactly that hydrogen ends up. We said when we did HX addition, for example, addition of HBr to propene, we end up with the bromide attached to the more substituted carbon of the alkene. Okay, and this is what they refer to as the Markovnikov product, okay? Also known as AKA Markovnikov. Okay, and so loosely defined, Markovnikov means the more substituted product, the product where the X group ends up on the more substituted carbon of the alkene. The problem with this nomenclature is twofold. One is that tells you nothing about mechanism, right? So if you want to learn things by Markovnikov, anti-Markovnikov, you're just memorizing, which stinks. The second thing is that it gets to be ambiguous very quickly. And so, there are instances where it's not clear if it's anti-Markovnikov, Markovnikov, say for like, we got 4 substituents on an alkene. How do you define the more substituted, right? And so, so because of those reasons, I'd encourage you to learn this, or memorize it, unfortunately, because it comes up, but I would encourage you to couple these definitions to mechanism so that you don't have to just, sort of blindly remember what Markovnikov means. All right, so anyway, so this was the previous reaction we discussed. We said it proceeds by an ionic pathway, right? So the first step is protonation of the alkene to give a carbocation, and then trapping by bromide, okay? So it turns out that if one takes the same reagents, okay, if we take propene plus HBr, all right, and now we're going to add a peroxide, okay, which is this species here. So has an OO bond, okay. Now the reaction pathway is different. So I end up with what we call the anti-Markovnikov product, or the product where the bromide is attached to the less substituted carbon of the alkene. So these reactions are typically, you use a little heat or light to get them going, and we wind up with this.
I'm sorry, what does it say on top of the arrow?
That's H nu for light,
Okay.
and then delta for heat. Yeah, because I'm pretty cool like that. All right, so how do we explain this? So we're getting a different product. This is the anti-Markovnikov product. Bromide attached to the less substituted carbon of the alkene, okay? And, so just stepping back for a second, anytime you've got two similar reactions, but they're giving a different outcome, that is a red flag that the mechanism has changed, okay? Because mechanism is what drives the reaction outcome. The formation of this more stable secondary carbocation when you protonate alkene is the reason that you get the bromide attached to the more substituted carbon, right? So if we change the mechanism, we sort of change the rules by which the system wants to play. And sort of the answer is that this second pathway proceeds by what we call a free radical chain mechanism. Okay. All right. So we need to introduce this of radical reactions. And so the way we're going to talk about these a little bit different. Okay. So what I first want to say is that radical transformations are characterized by sort of three parts. Okay, it's like, if you were go to see a Broadway play, the first act, the second act, the third act, there's always three acts to these things. All right, so what are they? So the first step or the first act is what we call initiation. And initiation is when we start to generate free radicals, okay? Okay, and so what do I mean by a free radical? So up till now, everything we've talked about has been what we call closed shell. So your carbons, your nitrogens, your oxygens have 8 electrons around them, right? Unless you're looking at a carbocation, in which case you have 6. It's always been an even number of electrons. So radicals are essentially any species, it can be any element that has an unpaired electron, has 1 electron, okay? Okay. And so that's the very general definition, and we can narrow it a little bit, or we can just be a little more specific. So for carbon, nitrogen, oxygen, their radical forms are going to have 7 valence electrons, okay? Okay. And so, all right, so I'm going to talk about the structure of the radicals and things in a second, so we'll just put that aside. The second act in the show is going to be what we call propagation. And this is where your starting material, SM, converts to product. Okay. And then the final act is what we call termination. And this is where 2 radicals are going to react. Okay, so in a termination step, 2 radicals will combine to form a stable species. All right, and so hopefully, as we go through this, this will start to make more sense. So,
Sorry, wait.
yeah,
Step 2. What does SM mean?
starting material.
Okay.
So whatever my substrate is, yeah. So propene for the example I showed you on the last slide.
Okay. Thank you.
Yep. All right. So let's go through that, the radical addition of HBr to propene in detail, sort of through the lens of these different steps. So I'll just redraw it here. Okay. And so the peroxide, ditert-butyl peroxide, is what we refer to as an initiator. Okay. And so I want to start generating these free radicals. Okay. Typically, to do that, we're going to add a bit of an initiator. There are lots of different initiators known. Ditert-butyl peroxide is one of them. Your book talks about AIBN. These are all things that can form radicals under mild conditions. And so in the initiation step, okay, you're typically going to irradiate the flask or heat it up. Okay, in this case, either one of these will work. The oxygen-oxygen bond, very weak bond, 36 kcals per mole. And so it doesn't take a lot to fragment that bond. And the way that it's going to fragment is by what we call a homolytic cleavage. And so when we were discussing, for example, acids and bases, we always pushed 2 electrons, right? When we had, a base attack a proton, it was 2 electrons. Then you took the 2 electrons in the acid hydrogen bond and pushed them to A. Here, we're going to push single electrons. And so to show that, I use this like fishhook or one-sided arrow. Okay. And so I'm going to take the electrons in the OO bond and have a fishhook going to each oxygen. And that tells me that I'm taking 1 electron from that bond, dumping it on one oxygen, another electron on the other. Okay. And so what I end up with are two of these oxygen-centered radicals, and we call these, tert-butoxy radicals, since the alkyl group is a tert-butyl. Okay, so that's step 1 of the initiation. I basically cleaved my initiator, the ditert-butyl peroxide, to generate these radicals. In the second part of the initiation step, that's going to react with HBr. Yeah, Caroline, do you have a question?
Yeah, I was just curious more generally about charge on the tert-butoxy radical, and like if there's like other, like I know that you only drew 1, but like if there's other electrons, like lone pairs, if that makes sense.
Yeah, it's probably good to draw them in. So they're normal oxygen when it starts. So you got 2 lone pairs on each oxygen, and those electrons don't move in this bond breaking process. So I can put those lone pairs in here. Okay. And then if you go through the formal charge, you should get to 0 because I got 7 electrons around each oxygen.
Wait, why would that be 0 if, wouldn't it be -1?
I'm sorry. 1, 2, 3, 4. Yeah, I've got 7 total. If you have the number in the bonding orbital, you get 6.
Okay.
Charge calculation goes to 0. Sorry. Yeah.
Okay. Sorry. Thank you.
Yeah, but the point is, there's 7 total, not 8. So it's got a partially filled valence. It can still take another electron, but it can't take 2. Okay. All right. So, and then in the second initiation step, that tert-butoxy radical is going to react with HBr. And because it has 7 electrons, it can only take 1 more electron. So we can't, dump 2 electrons into this. We want to add an electron to get an octet. And so to do that, we're going to again use the fishhook notation. We're going to take that single electron on oxygen, draw a fish hook, okay? And then I'm going to take a fish hook to the HBr bond, have that sort of go over in close proximity, and then another one to push an electron to Br. And so what I end up with then is OH plus Br dot. Okay. So let me just give you, while you're copying that down, let me say again what's happening in step 2 there. So the T-butoxy radical is going to attack HBr, okay? It doesn't have, previously we've seen like T-butoxy minus, we've seen like the alkoxide pick up protons, right? In that case, I've got 8 electrons around oxygen and a negative charge on oxygen. In this instance, oxygen has 7 electrons total, 6 if you're doing the formal charge calculation, and so the net charge is 0, okay? But the 7 electrons tells me that I want to pick up one more. I'd like to get to an octet. Molecules always, you know, first row, second row elements always want to get to an octet. And so the way I can accomplish that is I can attack the HBr bond, but I have to do it in a way that we haven't seen before, which is this homolytic cleavage. So I'm going to pull off the hydrogen and one of the electrons in the bond, and then kick that remaining electron back to Br. Okay, does everyone follow that? It's a little different than what we've seen before.
And would we have to write like ×2 or anything just because it's happening to like 2 T-butoxy radicals?
No.
No.
Yeah, you can just drop one of them. That's fine. Yeah. Okay, so that gives me Br dot. And it's just important to think about, you know, if you think about step 2, why is that favorable? You think about the bond dissociation energies. The HBr bond is relatively weak. It's about 87 kcals per mole. Okay, but the OH bond is very strong. It's on the order of 110 kcals per mole. Okay, and so that means that if you just consider bond enthalpies, I'm going downhill by about 23 kcals per mole, which is quite nice, quite a strong driving force. Okay, and this is why, you know, OH bonds are just very strong. You know, 110 to 115 kcals per mole, depending on what else is attached. This is why we talk about, you know, antioxidants in your diet. Essentially, antioxidants serve to quench any oxygen-centered radicals that form in your cells, because once you form that radical, pretty much every XH bond that it can go after is going to be weaker than the OH bond. So it starts cleaving those, and, you know, you get carbon-centered radicals on your DNA, and all sorts of bad stuff starts to happen. So anyway, these are very reactive radicals. They find the HBr, they cleave it, they make Br dot, and that completes the initiation. All right. And then the second DAC is the propagation. So all right. And so in the propagation, again, we're going to have 2 steps. We're going to have our Br dot that we formed in our initiation. Let me put in all the lone pairs here. That's going to find a molecule of alkene. Okay. I'll just make that CH3. All right. And the Br dot is going to attack the alkene. And again, the mode of attack is going to be new. It's this sort of this single electron pathway. All right. So bromide has 7 electrons around it. It wants to get one more. Okay. So it can't get that by doing a 2-electron pathway. So what it does is it pulls an electron out of the pi bond, okay, to make a CBr bond. And then there's one more electron that was in the pi bond that goes to carbon. All right. And so what you end up with then is bromide attached okay, with a radical at carbon. And then that is a carbon-centered free radical. Okay. And in the second, so the key with the propagation part of these reactions is that you always want to sort of regenerate what goes into it. So the starting material in step 1 should be formed at the end of the propagation section. And so the way that works in this case is that that alkyl radical, that carbon-centered radical, is going to find another molecule of HBr, and we're going to do the same type of transfer. So I'm going to move the hydrogen plus one of the electrons in the BRH bond. So bang, bang, bang. And that gets me here. Okay, so that's the propagation. All right. And so basically, when you run these reactions, the initiation occurs, you get the TB toxy radical, that reacts with HBr, you get bromide radical. And then you're sort of in the propagation regime where the system is just going and going and going over and over and over again. So bromide attacks the alkene, I generate an alkyl radical. The alkyl radical finds HBr, I generate product plus Br dot again. Okay, and that Br dot can go back, find the starting material, repeat the process. It just goes over and over and over again. Okay, like all good things, it must come to an end, right? And so the third act is what we call termination. Sounds rather dramatic, but it's basically going to be any step. There's a lot of different termination steps that you can invoke. The key is that you're going to invoke radicals going to closed shell intermediates. So going to intermediates with full octets, okay? That's kind of the only rule for a termination step. You know, whether or not that's a likely step, you know, what's going to be the dominant termination step, that's a matter, you know, for discussion. But so long as you have radicals going to closed shell species, you've identified a viable termination step. And so one example, so many possibilities. One example is to have two bromide radicals come together. To make bromine. Another example would be to have your alkyl radical react with Br dot to make a dibromide. Okay. But the key, again, the key for the termination is open shelled or species with unpaired electrons goes to closed shell. So species with full octets. Okay, that's basically the definition of a termination step. All right. I'm going to talk about the regioselectivity, so why bromide attacks the terminal carbon. But before I do that, let's open it up to questions about what we've covered so far.
I have a quick question. Is there any way to like determine what's most likely to happen, or like would we just be expected to like name every scenario?
No. You know, I think you know,
I mean in termination, like at the end.
yeah, in the termination step. Yeah, I know what you mean. So you want to basically have, okay, so let me give you sort of a more concrete way to think about it. So take two radicals involved in the propagation step and have them combine. Does that help?
Yeah, that makes sense.
So you could pick any two. You could pick two of starting material or two of the alkyl radical, two bromides. You can mix and match them, you know. And I'm glad you asked, because if you look at the propagation, what's happening? I'm going from radical on one side of the arrow to another radical on the other side, right? And then radical on that before that second arrow, and that goes to product plus another radical, right? So I'm always like radical to radical, radical to radical in the propagation, but the termination is radical to closed shell. That makes sense?
Okay. Yeah.
Okay.
Thank you.
Yeah. Any other questions?
Yeah, I just wanted to make sure for in step 2 to like 3 of, well, I guess first was like step 2 in propagation, in that like second part, is it that oh, sorry, my bad, the first part. In the first part, is it that the, can you see like that the double bond, one bond of the double bond is breaking apart in order to bond with the BR? Is that
Yeah,
what's going on?
exactly what's happening. Yeah. So the
Okay.
pi bond, it's the pi bond that I'm attacking. Okay. So that there are two electrons in that pi bond. And I'm basically going to take one of those and use it to bond to bromide. And then I've got one left over. And so because I attached the bromine to the terminal carbon, I just move that electron to the internal carbon.
Oh, so like the radical, that one free radical on the carbon is coming from breaking apart the double
Yeah.
bond.
Exactly. So this is this guy here. This was the electron in the pi bond that wasn't involved in bonding to Br dot. So that so another way to maybe say it is, if you count, you know, how many electrons are involved in this first step of the propagation step? Well, I've got one on bromide, right? And then I've got two in my pi bond. So when we look at the other side of the equation, I got to account for all of those. And so now I've got so 3 electrons total. So now I have 2 electrons in the CBr bond. There's got to be one more somewhere, and that's my radical.
Oh, okay.
Does that help?
Yeah, no, it definitely did. Thank you.
Okay. And then, you know, it's always good to think about thermodynamics. You know, why are we drawing this? What makes this possible? And it, you know, we're going from a CC pi bond to a CBr sigma bond. And it's a general truism. There are a couple exceptions, but generally, anytime you go from pi to sigma, you're going to be thermodynamically favored, because sigma bonds are just inherently stronger than pi bonds. Again, there are, you know, outliers, but generally speaking, it's always beneficial to make a sigma bond. So, all right. So let me just, I just want to say one more thing, which is that, so the propagation is like the engine, you know, it's like it's turning around and around and around to make the product. And it depends on the reaction conditions and you know what you're actually using and stuff. But to give you a ballpark, you're about 10 to the 4 propagation steps per termination. Okay, so 10,000, you can imagine, you know, you're going to get 10,000 turnovers to product before you get a termination. And why is that the case? We don't need to say too much about this, but for those of you that are curious, radicals, very high energy intermediates. You're not going to accumulate a flask full of radicals. These things form and react very quickly. And if you consider what's happening in the termination, it's 2 radicals coming together. And so I need to have 2 species that are at very low concentrations find each other in solution. And that's just an unlikely event. And so the more likely scenario is in the propagation section where you've got one very high energy radical intermediate reacting with a stable abundant molecule, in this case, the alkene or the HBr, okay? All right, so we'll spend a second talking about regioselectivity. So why does Br attach to the less substituted carbon? Okay, so I'm going to redraw substrate plus Br dot, and we'll consider the two modes of attack, okay? And so step one, or mode A, is that I could take that electron, have it attack the pi bond, and push the attack at the terminus of the pi bond, push the electron up to the more substituted carbon. Okay, and then mode B, so we'll call this mode A. Mode B is going to be attacking the more substituted carbon and push that lone electron down to the terminal carbon. Mode B. And so, okay, so these are the two possible products or intermediates that I need to kind of think about, all right? And just the same way that we said that, you know, carbocations, you have a methyl cation, you have a primary, secondary, tertiary. We use the same nomenclature for free radicals. So we would refer to the one on the left as a primary radical intermediate, and the one on the right as a secondary radical. Okay, and formation of the secondary radical is favored. And the $1 million question, of course, is why, right? And so there are two things that we need to think about. So one's kinetics and the other is kind of thermodynamics. And so kinetically, attack of bromide at the less substituted carbon in the alkene is going to be favored. And so when I say favored and kinetics in the same sentence, I mean faster, okay? And the reason is that if you think about bromide, you know, chlorine's about as big as a methyl group. And so bromide is bigger. And so it's this big bulky atom, you know, and it's got to get in and bond to carbon, okay? And carbon's, you know, self-evident, they're at the center of your molecules, right? You always have hydrogens or something else on the appendages. And so it's harder for that big bulky bromide to get in there and find that more hindered secondary carbon than it is to find the primary one at the end, okay? So we call that sterics. So sterics, or non-bonded interactions, favor attack of Br dot at the less substituted carbon. All right. So one of the reasons we form the secondary radical is that in that first step, it's just easier for bromide to attack the more accessible terminal carbon. Okay, is everyone with me on that? Okay, and then there's sort of a second argument, which is a thermodynamic argument. So talking about the stabilities of things, okay? And secondary radicals are generally going to be more stable than a primary radical. And does anyone want to venture a guess as to why? Yeah, Caroline.
Is it because you have like more distribution of charge because of resonance, whereas for like a primary radical, you don't have distribution of charge?
Yeah, you're close. So that primary radical, so recall hyperconjugation, right? And we said that hyperconjugation was basically what? Distributing the positive charge into adjacent CH bonds, right? And so this is going to be the same thing. Hyperconjugation is going to stabilize an adjacent radical. Another way to say it, overlap of a CH sigma bonding orbital with a radical is stabilizing. And so to understand that, we have to look at an MO diagram. So the secondary radical is more stable. The reason, hyperconjugation. I was not lying when I said this is, hyperconjugation is a third of chemistry, right? The other two are resonance and inductive. And so we're going to return to this hyperconjugation model now to understand why radicals, secondary radical is more stable. And so if you consider I'm just going to draw like the ethyl radical on this page. Okay. So here's the line drawing up top. And then now I'm going to draw it in 3 dimensions. So I've got the carbon on the left has the radical. Okay. Radicals are sp2 hybridized sort of with an asterisk. Okay. So we typically say, okay, this radical resides in a 2p orbital. And these are sp2H bonds. The carbon is sp2 hybridized. The asterisk is that typically we think of sp2 as being planar. In this case, there's some parameterization that occurs. So okay, and your book goes through this in a lot of detail, but basically, if you think about a carbocation, sp2 with an empty 2p orbital, there's nothing in that 2p orbital. There's no electron repulsion with the bonding orbitals, and so those things can go planar, no problem. Now, if I have a radical, I've got 1 electron in that 2p orbital. There's going to be some repulsion, and so the system has a preference to parameterize slightly, but we still regard these as sp2 hybridized. Okay, and so this is an example where the models that we use tend to fall apart a little bit. Anyway, this can overlap with an adjacent CH sigma bond. Okay, in the exact same way that we saw for carbocations. Okay, so this is the beauty of this interaction, is like this crops up, adjacent orbital overlap just comes up everywhere. And like, if you can think about these, what these bonding diagrams look like, you can reason your way to the right answer. So we've got a filled sigma CH bonding orbital, coplanar with my half-filled 2p orbitals. And so I wind up with a system with 3 electrons. Okay. And so let me draw the MO diagram over here. So here's C2P. All right. Sigma CH is going to be lower in energy because it's a bonding orbital. Okay. This has 1 electron. This has 2. Okay. And then we're going to let them mix. And so just addition and subtraction. So C2P plus sigma CH, C2P minus sigma CH. okay? And then here's the rub, is that now I've got 3 electrons, right? And so 2 go into that bonding interaction, 1 goes up top into an antibonding orbital, and you might be saying, wait, that's bad. It is bad, but we've got 2 electrons now in a lower energy orbital. And so the gain that I get from moving those electrons down, both of them, more than offsets the decrease in stability that I get from putting an electron into an antibonding orbital. And so the bottom line is that the net effect is stabilizing. So okay. So 2e minus move to lower energy orbital. 1 electron moves to higher energy orbital. But the net effect, the overall effect, is one still of stabilization. So if you add up the energies of the electrons before and after mixing, even though individually one of them goes up, the 2 going down results in a net gain. And so this is still a stabilizing interaction. Okay. And so it's strictly analogous to what you guys saw with carbocations, right? And so if I drop this electron in the 2p orbital up here, I've got a carbocation. I drop it from this diagram. I drop it from that from that orbital. It looks exactly like a hyperconjugation in a carbocation. It's exactly the same interaction. We just add another electron to it. Okay, does that make sense? So hopefully you see the continuity here. All right. And so this stabilization then is manifest in the homolytic bond association energies. So okay, so if you consider, let's make a little table. These are our radicals. We've got a tertiary, secondary, primary, methyl. I'll draw the structure here. Okay, so tertiary radical has 3 carbons attached, secondary 2, etc. We can look at the other side of that sort of equation, which is the corresponding alkane. And so drawing those hydrogens, and then we can ask the question, what is the homolytic bond association energy? What are the CH bond strengths in these alkanes? Okay, and what we find is that the tertiary is the weakest. So this is kcals per mole. Then comes the secondary, right? Then comes the primary, and then finally methyl is 104. Okay, so when I measure homolytic bond association energy, I'm taking the bond of interest, cleaving it homolytically, putting an electron on one atom, putting an electron on the other atom. Okay, in this case, we're talking about cleaving CH bonds homolytically. So for each substrate, I'm going to put an electron on hydrogen, so that doesn't change. But then what does change is the carbon that the other electron becomes attached to. And so as that carbon becomes more stable with the radical, the corresponding bond becomes weaker. It takes less energy to cleave that bond. Okay, and so we see that the tertiary CH bond is the weakest. Put another way, tertiary radical is the strongest. Okay, or is the most stable. Okay. The other thing I want to point out is sort of the deltas, the changes in kcals between the stabilities of the radicals. You can see here that, we're only at 3, here we're at 4, here we're at 4, right? If we think back on carbocations, we said, tertiary to secondary is about 15 kcals per mole, and secondary to primary is similar, right? I think it was like 14 for tertiary to secondary, and then maybe 16 or 15 for secondary to primary, right? And so why are those gaps much bigger? And you can go back and you can think about your MO diagram and say, well, I know that when I make this type of diagram here with a carbocation where I've only got 2 electrons, both of those electrons go down into a bonding orbital. I get a lot of stabilization. When I do this with a radical, I've got a 3rd electron that I need to find a home for, and I can do that, but it winds up being in an anti-bonding orbital, and so the net stabilization is less. And so that, my friends, is why the deltas here are smaller. So that's a direct reflection of the fact that the energy of one of these electrons has to go up. The system as a whole is still going down, but it's not down by the same degree as you get with the carbocation, where you lose that 3rd electron. Okay. Does that make sense to everyone? We got 2 minutes. That's pretty much all I wanted to cover. So I'll just stick around for questions and then take a 5-minute break and then office hours.
Yeah, I had a question. In the, do you mind if we go back to the when we were talking about the how to form the radicals, like in the termination step?
Yeah.
So I was a little bit confused as to why there were like 2 different examples, and yeah, I don't really get where the top example came from and why there's those 2 Br atoms.
So I think you're asking, where does the second Br dot come from? Is that right, Wendy? Yeah. Okay. Yeah. So, important to remember, like these reactions aren't happening in serial. So you're going to generate a bunch of initiator, and that's going to find, so you're going to have, a collection of T-butoxy radicals. That's going to find HBr. You're going to generate several equivalents of Br dot. And so at any given point in time, the concentration is low, but there's a finite concentration of Br dot floating around. And so if 2 of those can find each other, then you can terminate. So I think maybe it might be that the equation is totally unbalanced now, which is true. Sort of have to put that aside to show another Br dot coming in from, sort of another propagation cycle. Does that help?
Oh, so it's the second Br is coming from another propagation cycle, and that first Br, is that just like coming from, like, I guess, for instance, that first step in propagation where you have, no, JK, I don't know where the first Br is coming from either.
Yeah,
Where's the first BR?
Yeah, it's on the last slide. It's coming from the initiation. So down here at the bottom. So the T-butoxy plus HBr. So that's one spot, but then the other spot is oops, let me go back to there. Is here in the second step, right? So when I react the alkyl radical with HBr, I regenerate Br dot.
Okay.
So yeah, another way to think about it is like this. Imagine, the reaction flask is like this ball of like silver beads, and the Br dots are red beads. At any point, let's say you've got 10,000 silver beads in there, you're going to have like, I'm just totally guesstimating here, 5 or 10 little red beads that are Br dots running around, right? And like every so often, it's not likely, but every so often, those are going to find each other and make Br2.
Okay. Yeah. Thank you.
Okay. All right. If there's any other questions, just hold them to office hours. I'm going to take a quick break and then we'll come back.